Okay, so welcome everyone to the, this is the last day of the workshop and the first session. And the first speaker is Vincenzo Alba from the University of Amsterdam, and he will talk about entanglement dynamics and dissipation. Vincenzo.
Okay, so actually, so before starting, let me thank the organizers for putting together this nice workshop and for inviting me, of course. And I apologize if I could not attend all the talks, but I'm moving, so it's busy time. Okay, sorry about that. So today I want to talk about entanglement dynamics and dissipation. And recent progress that I think we made in this interesting area of research. And let me start with an outline. So the goal that you should have in mind here is that ideally we would like to describe how quantum information and entanglement related quantities they spread in integrable systems in the presence of dissipation. So why, on the one hand, we know a lot on about what happens if you have unitary dynamics, so out of equilibrium situations without dissipation, but on the other hand, in the presence of dissipation, which is very relevant for describing real life, we know very little. So, this talk is naturally divided into two parts. In the first part, I would like to address what happens if you have a quantum many-body system, which is out of equilibrium, let's say, for instance, after a quantum quench, and there is a global dissipation in the system, meaning that there is an interaction with the environment, with some environment, which involves all the sides of the model, of the system. And in this part here, I would like essentially to discuss only free fermion and free bosonic models for the simple reason that these are the only ones that we have been able to tackle so far. So we have only results for free systems. And so the main idea here is to combine a simple, hydrodynamic approach, to use a simple hydrodynamic approach, or also known as quasi-particle picture. And what I want to show is that it's possible to use this picture to describe quantitatively the dynamics of entanglement and entropies or mutual information in free fermions and free boson models in the presence of dissipation. So the take-home message is essentially that I believe that for generic quadratic systems, after generic quenches and the generic linear dissipation, and this is very important, we are able to provide, we provide a formula that describes the evolution of entanglement-related observables. This would be the main part of the talk. And then the second part would be about local dissipation. So what happens if the source of dissipation is localized? So instead of having a dissipation that acts locally, you have a localized source of dissipation. So I must say that I have a lot of material. So let's see what I can cover during the talk. And then I think I should apologize in advance if I'm not able to cover everything that I promise. So in this second part, essentially, again, I will focus on dissipative impurities, and I will provide exact results for free fermion models. So I will be able to describe the steady state that arises due to this impurities, which is not so new, I would say. Perhaps something that is more new and interesting is that it's possible to provide analytic formulas for the evolution of entanglement entropies or mutual informations and so on and so forth. Okay. So, to start, I think something that I should stress, which is extremely important, is that it's very difficult in general to characterize the amount of entanglement that is stored in a quantum many-body system. And the simple reason is the fact that in the presence of dissipation, the global state, the state of the system, is not pure anymore. So you are dealing with a mixed state. And for mixed states, so the usual quantities that we employ every day, so for instance, the von Neumann entropy or the Renyi entropies, are not good entanglement measures, okay? So they are not sensitive to the quantum entanglement only, but they also contain information about the fact that the system is in a mixed state. So even though these quantities are very easy to define, so you have your global system, which is, let's say, you divide into two parts, A and the complement A bar, and then you can easily construct these quantities from the reduced density matrix for your subsystem of interest. And then the question that you would like to ask is, what is the entanglement between A and the rest? Now, for mixed states or for quantum many-body systems in the presence of dissipation, these quantities for Neumann entropy and Renyi entropies, they do not characterize the quantum entanglement, but they contain information about quantum entanglement, but they contain also some spurious correlations, information about spurious correlations, which are not genuine entanglement, but consequence of the fact that the state is in a is mixed. But the good news somehow is that you can, there are good entanglement measures. So, and one of the most important ones is the logarithmic negativity. So this logarithmic negativity has been invented by Vidal and Werner long ago, and its definition is a bit cumbersome. So indeed, it's not a very easy quantity to compute or even to measure. So what you have to do essentially, you start from the reduced density matrix for your subsystem A, okay, or for for the full system. And then, sorry, here this A shouldn't be there, sorry. So you start from the from the density matrix of your mixed state, and then you choose a basis E and E bar for A and A bar. And then you define a rho transposed, partially transposed, which is obtained by simply taking the partial transpose with respect to the degrees of freedom in, let's say, in one of the two subsystems. So let's say A bar. In principle, you have a matrix. This is something that you can do very easily. And then you look at the eigenvalues of this object, this rho partial transpose, and then you define the trace of the absolute value of this, the sum of the absolute value of these eigenvalues, and then you take the log. This is the negativity, and this is a good measure of entanglement, of the entanglement that is shared between A, your subsystem A, and the rest. Now, this quantity will be relevant towards the end of this talk, but I think something that I want to convince you about is that these other quantities that a priori, I mean, this Renyi entropies and especially the mutual information that you define out of them, even though in principle they are not sensitive to quantum entanglement, in practice they work, I mean, as not as bona fide entanglement measures, but they are pretty useful also to understand how much entanglement is there in the system. Okay, now in the rest of the talk, I mean, the goal is to deal with to understand what happens to these quantities when you have a system which is out of equilibrium and in the presence of dissipation. Now, let me review for a moment what happens if your system, if the dissipation is not there, okay? If the dynamic, yeah.
Vincenzo, just one clarification. In this definition of the partial transpose, the A subscript is not there, and this EI, I mean, you have on the right-hand side both EIs, it's EI and EK, is that right?
Yes, sorry, the indices are a bit wrong, yes. Yeah, sorry. There is no A, and you have EI, E bar L. I mean, you take, essentially, you have a basis for subsystem A and the basis for A bar. And then you switch the indices or the basis that correspond of the basis that correspond to A bar. This is the correct definition. Sorry, there is a mess. Yeah.
Okay, thanks.
Yeah. So this rho is the density matrix of the full system, which is mixed. And then you have a basis for subsystem A. You can write it in the basis tensor product of basis of A bar. And then you switch the indices corresponding to the basis of A bar. And this defines the transpose. Now, this object has, the eigenvalues of this object are not positive definite anymore, unlike for the density matrix. This is why you have to take this absolute value. And then you can show that this quantity is a good entanglement measure. Okay, now, so before dealing with dissipation, I want to review briefly what happens in the unitary case. So in the unitary case, so for integrable systems, at least, there is a powerful hydrodynamic description of the entanglement dynamics. So first of all, so if you take a many-body system and you drive it out of equilibrium, for instance, doing a global quench, what happens is that typically you have a robust entanglement production. So for instance, if you look at the von Neumann entropy, it grows linearly with time at short times, and then at long times it saturates, right? This is very well known nowadays. So but I mean, this can be understood in integrable systems, and this was done by Pasquale Calabrese and Cardi in 2005 by using a simple quasi-particle picture. So this quasi-particle picture works as follows. So you have your system, and then you drive it out of equilibrium by doing a quench. And then essentially what happens in this picture is that there is a production of pairs of entangled quasi-particles all over the system. So these quasi-particles, quasi-particles that are generated near each other, so they form a pair, and they are entangled. But you have also, quasi-particles that are created far away, they do not share entanglement between them. These quasi-particles behave as free particles, so they are free. And as they spread, they propagate this entanglement through the system. So more specifically, at a generic time t, so you have your subsystem A, if you want to know the entanglement about between subsystem A and the rest, what you have to do, you have to count the number of entangled pairs that are shared between A and the rest. And since these quasi-particles behave as free particles, this you can do quite easily. And so if you do it, you get this behavior. So at short times, the von Neumann entropy of A grows linearly. Then at long times, so if your subsystem A is finite, at long times, the von Neumann entropy saturates. And it becomes proportional to the size of your subsystem A. Now, this picture was, let's say, invented in 2005. And at this level is only a cartoon picture because it explains well the qualitative features of the von Neumann entropy. But you would like to take this picture and apply it to get quantitative predictions for macroscopic integrable systems. So like the XXZ chain or XX chain or whatever. Now, this can be done. So it was done before for free fermion models. So for free fermion models, you can actually you can derive analytically this quasi-particle picture. So our main contribution in 2017 was to show that this can be actually generalized to generic interacting integrable systems. Okay, and in fact we conjecture here this formula. Okay. Now, this formula describes the full evolution of the von Neumann entropy of a subsystem A, okay? And it has two terms. So there is a one term here, which is proportional to time, and it acts, it's non-zero at short times. And then at long times, this term is not there anymore. And you have this term here, which tells you that the von Neumann entropy is proportional to the size of A. Okay, here I'm considering subsystem A, an interval of length L. Now, this formula contains two terms which are important. So this S of K and this V of K. This V of K is the velocity at which these quasi-particles travel through the system. And this S of K is nothing more than the thermodynamic entropy of the generalized Gibbs ensemble that describes the steady state after the quench. Okay, so here the situation that you have in mind is that you take a system, you perform a quantum quench, and what happens if the system is integrable is that at long times, if you look at local properties of the system, they are described by an equilibrium ensemble, which is a generalized Gibbs ensemble. this generalized Gibbs ensemble has a thermodynamic entropy, and this is what enters in this formula here. These velocities V are the velocities of the excitations that you can create above this thermodynamic state, this thermodynamic ensemble. So this looks complicated, but actually for free systems, this becomes much simpler. So essentially this V of K is the group velocities that you have. So you have a generic quadratic system, you diagonalize it, you get single particle energies, the energy, the dispersion of the model. This V of K is the group velocities. Okay, so the derivative of the dispersion epsilon K with respect to K. And this is still the thermodynamic entropy of the GG. Okay. Now the question here, something that I should say is that so this formula is nice because actually tells you that the entanglement dynamics doesn't depend on the full information about the quench. So it depends only on thermodynamic information. So in this sense, this kind of formula has some universality. Okay, it depends only on thermodynamic information about the system. It doesn't depend on the details of the initial state. Okay, on all the details of the initial state. Now, the question here that I would like to address is it possible to generalize this formula if on top of the unitary dynamics, we also add dissipation? Of course, there are, modeling dissipation is a very hard problem in general. So you have to restrict yourself to a well-defined framework. And here, the framework that I want to use is that of the Lindblad equation. Okay, so I have a system which interacts with some bath, but essentially, I model this interaction with the bath by using the Lindblad equation, okay? Which is also nice because you can also show. I mean, this is well known that this is the most general linear way of modeling dissipation interaction with the environment. Okay. So here you see the typical Lindblad equation reads as follows. So you have an equation that tells you how the density matrix evolves with time. And then, of course, you have the usual unitary evolution. And then you have this term here, which is encoding dissipation via this operators L. Okay. And by choosing this L, you can essentially model different types of dissipation. And you see here there's no I, so this means that this dynamics is not unitary anymore. Now, okay, indeed. Now, I mean, there are a lot of results about Lindblad dynamics, and here I want to summarize at least I would say 3 classes of results that are available. At least to my knowledge, these are the only cases where you can, for which you can address this Lindblad equation analytically. So one very well-known one is if you have a quadratic Hamiltonian plus linear dissipation. So if you have a dissipation which is a linear in the fermionic operators and the Hamiltonian is quadratic. So for instance, here I consider an Hamiltonian written in terms of some Majorana fermions, and also some dissipation, which you see is linear in the Majorana operators. So this L are just some numbers, some parameters. Then you can go very far because actually you can essentially solve the problem. The problem remains quadratical in a sense. You can solve it, and this I think is I mean, this for many cases is called third quantization, and of course one of the great I mean, some of the best results were obtained by Tomasz Prosen. So there's something which is a bit surprising is that even though there are situations in which, even though the problem doesn't remain quadratic, it's still possible to get a lot of results by, I mean, with the computational cost, which scales essentially linear instead of exponential with the size of the system. So, for instance, if you put free fermions with incoherent hopping or dephasing, you can look at the 2-point function of the expectation value of the 2-point function for the fermions. And you can write down a set of equations, okay, for this 2-point function. And essentially, you can reduce the problem to solving a system of L equations. So to fully determine the dynamics of the 2-point function. This has been done for several models. So for instance, for incoherent hopping in this paper. And it's actually very, very useful as well. But I mean, at least if you are a person who is interested in integrable systems, what you would like to do is to really consider, I mean, to solve completely, for instance, the spectrum of the Liouvillean that determines the evolution of the observables. So you would like really to solve completely the problem. And this is something that became I mean, there have been a lot of efforts in the last couple of years. And here I list there is an incomplete list of results. I apologize with the people that are not in the list. Okay, now in the rest of the talk, I would like to start with a very simple example. And by working with this very simple example, I will derive a formula valid for free fermions with linear dissipation. And then I will show that this formula is actually quite general. Okay, even though the structure is derived by considering this very simple example, then I will convince you that this is quite general. So here, the problem that I want to start discussing is the case of a simple free fermion hopping model. So this is simple Hamiltonian here, which describes hopping fermions. And this you can easily diagonalize it by doing Fourier transform. You get this single particle dispersion. You can also get by taking the derivative with respect to k, the velocity of the fermions, the excitations. And then I want to add gain and loss dissipation. So gain and loss dissipation means that essentially you remove or add in an incoherent way the fermions, okay? And these are described by these operators here. So this operator cell here. So you see one operator is proportional to C dagger at site J, and then the other is proportional to C. And then there is some rates at which you add or remove fermions. So this is quite simple. And the reason why it's simple is that essentially this dissipation is diagonal. So in fact, what happens is that if you consider the correlation matrix, so the G, so this is the expectation value of C dagger I Cj for a subsystem A, what happens is that its eigenvalues evolve in this very simple way. So you can consider the problem without dissipation, okay? You can take the 2-point function, you can calculate its eigenvalues, and these are this lambda tilde, okay? If you, on top of that, you add this simple dissipation, what happens is that essentially you shift and rescale these eigenvalues because this dissipation is diagonal. And you get these lambdas. So these lambdas are the eigenvalues of G, are the eigenvalues of G in the presence of both unitary dynamics and dissipation. And these lambdas, tilde, are the eigenvalues of G in the case without dissipation. And this factor here, so this B is just e to the minus the sum of the rates, and this n infinity is this factor here. And in fact, I mean, this also gives you essentially an evolution. Essentially, you can decouple all the sites, okay? And you can get the evolution from for the density of the fermions just by solving the problem with a single site, okay? So in fact, if you have, so imagine you have a density of fermions n0, okay? And then you want to see how this evolves under the combined action of unitary dynamics and dissipation. And this equation here gives you how the density evolves. Okay. At equal infinity, you get this density n infinity. Okay. And you have these factors around here, B's that I introduced here. Okay. So the problem here is extremely simple. Now, what I want to do is to show that, I mean, with this simple kind of dissipation, you can easily derive how the von Neumann entropy, or more generically, the Renyi entropies evolve. And here I consider now a non-trivial quench. So I have free fermions, and the initial state is a state here. So this kind of nil state in which I have 0, 1 occupations, okay? So 0 occupation on the even sides, and full occupation on the odd side. So this is a kind of nil quench. Now, essentially, the main observation is that the main quantity that I want to use is this correlation function for the fermions, G, you see. And what I need to know is that the von Neumann entropy for subsystem A is written in terms of this correlation function G only. Okay, if I have this correlation function, since the problem is quadratic, I can derive the von Neumann entropy. So if I have the evolution of this G, I have the evolution of the von Neumann entropy. Okay, now but here the main observation is that I told you in the previous slide is that so the eigenvalues of this G when you have dissipation are simply related to the eigenvalues of the G in the case that I have in the case without dissipation. Okay, and this allows me to play this trick. So I can construct. I know analytically, because it has been worked out several years ago, how the trace of any power of this G tilde here means that there is no dissipation, so the dynamics is unitary. So for any n, I have essentially an analytic formula for how this object here evolves. So since the eigenvalues, if I add dissipation, the eigenvalues to change in a simple way, what I can do is to get an analytic formula also for this trace of G. Now here I have G. Okay, so G is with the dissipation. And then since I know these objects for any n, I can do an analytic continuation if you want. I can get an analytic formula for this object here, which is the von Neumann entropy or the Renyi entropies, okay? So if I do this, essentially what I end up with is this formula here. Now, this formula is the type of formula that we want, okay? So this formula describes how the Renyi entropy with index n of a subsystem of length L evolves with time. Now, this formula has a lot of information in it, so let me comment about this formula. So there is an integral over momentum, which means that you are integrating over the different quasi-particles that you can create after the quench. Then there are two terms. Now, there is this term here, you see. This term is a kind of volume term. So it acts all over the place in the system and is proportional to L. And this term is due to dissipation only. So it somehow parameterizes the incoherent action of the bath on the system. This other term here is as this mean function here. And this term, the structure of the term here, is the same as in the case without dissipation. In fact, this term here describes the evolution of these entangled pairs. But the prefactor here, of course, is not the same as in the case without dissipation. So it contains information about that you have dissipation. And precisely this information is in this term here, which is the same that you have here, you see? Now, so let me comment about this. So let me say something. Okay, something interesting is the following. So from this piece here, essentially what you learn is that the effect of dissipation is to diminish the correlations, the entanglement, if you want, between these entangled pairs. So you see here, there's a minus sign. So in the case without dissipation, this SN mix goes to 0 and you are left with this. This drops out and you remain with this. So you have the usual quasi-particle picture for the unitary case. Now, this formula holds in a scaling limit. Okay, so the scaling limit is defined as follows. So you have to take time goes to infinity L, the size of your subsystem goes to infinity. And then the dissipation has to go to 0, because if you keep the dissipation rate finite, essentially, I mean, the dynamics is trivial. You immediately reach the steady state. Okay, so it's not very interesting, I would say. So you have to send the dissipation rate to 0, and then you have to keep this ratio T by L and the gamma times L fixed. So the dissipation, this is the usual scaling limit that you have in the unitary case. Okay, it's the hydrodynamic limit. Now, these functions S here that you have are defined here. And essentially, this function S depends on the density of fermions. So this N of K is the density of excitations. And I mean, this formula here is essentially the usual expression for the thermodynamic entropy in a free fermion model. So if you have a free fermion model, essentially any thermodynamic state is characterized by the probability of occupying the single particle energies. In the thermodynamic limit, these occupations become indeed probabilities. So you have this N of K, which gives you the probability of occupying the mod K. And this entropy essentially counts the number of ways of occupying these single particle energies that in the thermodynamic limit give these functions N of K. Now, in this specific case in which you have this initial state and the Hamiltonian is just this tight binding Hamiltonian, these two functions, S mix and SYY, which stands for Yang, okay, it's not very important, take some very simple form. So this S mix is given here. So you see, you have this function here, evaluated at this density here, and this one here means that essentially the initial site is fully occupied. Okay, the initial value of the density when is fully occupied is 1, and this is the entropy obtained from the density in which the initial value is 0. So essentially, and you take the average of the two. Essentially, this means that this incoherent term, to calculate this incoherent term, essentially you can decouple the sites. Okay, so the zero side, the sites that are initially empty evolve independently. The sites that are initially occupied evolve independently, and then you calculate independently these two entropies, and then you take the average. On the other hand, this term here is this one here. So you see, so is again this thermodynamic entropy calculated from the density, but now from the N of K. But now the initial site, so the initial density is 1/2, and this tells you that essentially this term is quantum, because what happens is that here, due to the fact that there is hopping, which is quantum, this initial discontinuity is mirrored out, and then every site is half occupied due to the fact that you have hopping. And this is the effective initial density that you have to use here. So it has, I mean, this formula for this specific case, it has a very simple physical interpretation, I would say. But remember, okay, we got this formula here. Now, the question is, we want first to check it. And here I show some checks, okay? So this is, for instance, the von Neumann entropy as a function of time for the hopping Hamiltonian in the presence of losses, okay? So you remove fermions. Now, these symbols are exact numerical data, and this dashed line is the formula that I showed in the previous slide. And you see the agreement is perfect. However, a caveat is the following. So this von Neumann entropy, as you see from this formula, has this volume law term. And this volume law term is the dominant one, okay? So this is the dominant one. So this is, if you want, the most interesting, because it contains this information about these entangled pairs. So a good way to remove the effect of this volume term is to consider the mutual information, okay? So this combination here. So you take the entropy of A plus A bar, and then you subtract the total entropy, which is non-zero because you have dissipation. If you are in the unitary case, this total entropy is zero, here is non-zero. And now you can see that this mutual information is only sensitive to this second term here. And this is the sense in which I was saying at the beginning that the mutual information contains information about somehow the entanglement, because it depends only on this term here, which is the same that you have in the unitary case, and which is essentially sensitive to the presence of these entangled pairs. And here I show this mutual information, again, for the case, here actually for the case of in which you have both gain and losses with different rates. So these are, again, the symbols, and this dashed dot line is the theory prediction. So is the theory prediction that you get from this formula. And you see, again, this is quite in good agreement. Okay. Now, you can also look at different types of dissipation. So here again, I have sorry, and you can look at the negativity. So the negativity is, as I said at the beginning, a good entanglement measure, unlike the mutual information. Okay. But I mean, let's go back for a moment here. So what we have is that the mutual information essentially grows up to a time scale which is proportional to 1 over gamma, and then it decays exponentially to 0. This is the behavior of the mutual information. If you take the negativity, which you can also compute, essentially you get the same behavior. So you have that it grows in a very similar way, and up to a time, again, which is proportional to 1 over gamma, and then it decays exponentially at infinite time. Okay, this is what you get for gain and loss dissipation, which is the type of dissipation that I introduced before. You can also construct it for more different types of dissipation. So for instance, for dephasing or incoherent hopping, but you still get the same qualitative behavior. So you see, if you compare it with the mutual information, essentially qualitatively is the same. So here a caveat that I should make is that for incoherent hopping and dephasing, the evolution is not quadratic anymore. So in principle, it's very difficult to compute entropies or negativities. On the other hand, as I mentioned at the beginning, it's easy to compute the two-point function of the fermions, and then you can pretend that the system is quadratic, and you can compute these entropies or negativity. But this, if you want, is something arbitrary, okay, or maybe it's an approximation. I mean, it's not under control, okay. So these results for incoherent hopping and dephasing, you shouldn't take them. You should take them with the caveat. So I don't believe this is really the true negativity, because I'm neglecting the fact that the system is interacting. Okay. And also you can show that there is some nice scaling. Okay, so there is a scaling both for the negativity and for the mutual information. So for instance, you can take this scaling plot. So you can take the negativity and then you can multiply by gamma, and then you can plot versus a rescale time, which is gamma times t. You have to take, of course, for different type of dissipation, the relevant gamma. So if you take losses, you have a gamma minus. For incoherent hopping, there is a gamma hopping rate, and for dephasing, there is a gamma dephasing rate. And then essentially what happens is that if you increase L, you go to longer times, and then you send the dissipation rate to 0 as, let's say, 1 over L. What happens is that all the curves, they go on top of each other. So you have a scaling regime. In all cases, so for gain and loss, hopping, dephasing, and the same happens for the mutual information. Here, for a very important reason, I show the Rényi mutual information with the Rényi index 1/2. And the reason why I do this is that in the unitary case, so in the case without dissipation, you can actually show, and it has been shown here, that in this scaling regime, essentially, the negativity becomes the same as 1/2 the Rényi entropy with the Rényi index 1/2. So, but here in the case with dissipation, this is not the case. So these two quantities are different, unlike the unitary case. Okay. Now, the main question is how general is this result? Because, I mean, the system that I considered and the dissipation that I considered, they are both quite simple, okay? So it's a very, I would say, trivial setup. Diagonal dissipation and simple hopping Hamiltonian. So now what I want to show somehow is that this result is quite general. Okay, in fact, it holds generically for free fermion and free boson models. So here I have in mind to take a generic free model that you can bring into diagonal form by a combination, as usual, of Fourier transform and Bogoliubov transformation. You can bring it to this form. So this B are, I mean, the Bogoliubov operators, and this epsilon, the single particle dispersion. Quite generically for a system that you can, fermionic system or bosonic system that you can bring into this form, I want to argue that this formula essentially is the same. Okay, now, and here the strategy that I want to follow somehow is first by guessing, you see, I mean, this formula depends on these two parameters. So it depends on this S, on this S mix and S yang. So first, I would like to guess these two parameters. So if I'm able to make an educated guess about these two parameters, I can try to use this formula and see if it's valid. And then let's say later, I will show that in one case, for the Ising chain with the arbitrary linear dissipation, I'm able to derive analytically this formula here. But for the moment, let me guess what enters in this formula. And here, I mean, I use two observations, okay? So the first observation is that in the unitary case, essentially, this S and yang is determined, is the yang entropy that I construct from the density, from the occupation of the Bogoliubov modes that that diagonalize your free model. On the other hand, this S mix in the unitary case is not there. Now, the strategy is the following. So, in the unitary case, essentially, what is important is the density of Bogoliubov modes that diagonalize the free model. What happens in the presence of dissipation? In the presence of dissipation, essentially, you can try to determine some operators B, which are eigenmodes of the Liouvillean. Okay. So you have your Liouvillean, which encodes unitary dynamics plus dissipation, and you can look for the modes of this Liouvillean, this beta. And then the natural idea is that from this beta you can construct the occupations, so the occupation density of these modes that you call rho. Okay, so this is the analog of what was the n of k in the previous slides. And then once you have this rho, you can construct this yang entropy. And this would be what you have to put here, okay? On the other hand, this S mix is quite easy to get because you can consider the entropy of the full system. So,
sorry, Vincenzo.
Sorry?
What is gamma k? Next slide.
Okay, yes, sorry, I should say, yeah, I should be more. Okay, so
actually, what is the Lindblad that you're applying here? Is still the loss gain, or it's a generic?
No, this is a generic. So imagine you have a generic Liouvillean, and then you have to find the eigenmodes of this Liouvillean. Of course, the problem is still quadratic, and this epsilon is so. In fact, what you get is that if you do this, I mean, if you try to do that, what happens is that, well, at least for the cases that we explored, which means Ising with quite generic linear dissipation, or free bosons with dissipation, you get a formula like this. So you get that this, I mean, here you have the single particle dispersion. This is the same dispersion that you have in the unitary case, I mean, without dissipation. And these gammas are some functions that you have to determine that depend on the dissipation. This is why I call them gamma, because somehow they contain information about the dissipation rates.
For quadratic dissipation, that's the only.
For quadratic dissipation, yes.
Thank you.
Yeah. So I was saying, so how do I determine this S mix? So this you can do, I mean, in a very simple way. So you can imagine of looking at the entropy of the full system. So if you look back at this formula, the entropy of the full system does not depend on this term here. And this is because this term, you see, I mean, if you essentially, it's the same as in the unitary case. So it contains information about the quasi-particles that are shared between your subsystem and the rest. But if your subsystem is the full system, this term is 0. So the entropy of the full system contains information only about this S mix. So it's proportional to volume, and it is this integral of this function. But if you have a generic quadratic system, the entropy of the full system, the entropy is constructed from the 2-point function. Okay, so and essentially, if you have the full system, essentially what you have to do, you consider the 2-point function. So for instance, for the Ising chain, you have to take the 2-point function of the Majorana operators. Okay, and then you go to Fourier space. This 2-point function, which would be a L by L matrix, become if everything is translational invariant, which is what we consider here, become a 2x2 matrix, which depends on momentum. And then you can, from this 2x2 matrix, you can construct the entropy. Okay, this is a simple formula, because everything here, the most complicated thing is 2x2 matrix. And this gives you this S mix. And now you have both ingredients, right? So you have both ingredients, you plug them into the formula, and you see what you get. So, and here, let me show you some results. So this is the case of the harmonic chain. Okay, so the harmonic chain is defined by this Hamiltonian. So this is essentially, so P and X are canonically conjugated variables. But the important point is that you can map this Hamiltonian to free bosons. So it's essentially a chain of free bosons. And then you consider a generic non-unitary dynamics, or generic Lindblad evolution. And so this is written here. And here the dissipation is parameterized by this matrix C. And these R are essentially these X and P variables arranged in this way. And now you can choose this dissipation the way you like. So for instance, you can consider even non-local dissipation. So here we take Cij of this form. So the sum over alpha is a sum over different sources of dissipation. And this C alpha ij, you can write them in this form. So this C alpha are these matrices here. Okay, this, this F is essentially describing, is describing how this non-local dissipation decay with the space, okay, with the distance. And then these gammas are the rates. And you see this C here encodes different type of dissipation. So for instance, this C plus and minus means that essentially you add or remove bosons. And this Cx means that the dissipation here, essentially you have the X operator or the P operator for this other type of dissipation. So it's quite general. But importantly, it's not local, okay? So then you want to see the evolution after a quench in this model in the presence of dissipation. And here I consider a mass quench. Okay, at the beginning you prepare the system into the ground state of this Hamiltonian for m is the mass of the oscillators, m equal m0, and then you suddenly change m0 to m. And then here you can look at this quantity here, SL pair von Neumann, which is essentially twice the mutual information of a subsystem A. And here you see, I mean, you have these different curves, which are exact results. And then you have this dashed line, which is this prediction. Okay. So this prediction for this quite generic form of dissipation, no local one, it works. Of course, it works in a scaling limit. So you have to send, again, L to infinity, 2 to infinity, gamma to 0, and then rescale everything accordingly. Even though you see, even for finite L, it seems to work quite okay. So you can actually do an extrapolation. So you can fix here, you can put yourself here and then see how the deviations scale as a function of 1 over L. And then you see you get a nice 1 over L behavior, and the extrapolation here is in agreement with is essentially the theory prediction. Okay, now this is for the harmonic chain, so a bosonic system. You can also do, you can also study the Ising chain. Okay, here I think I want to be quick because I think I'm running out of time. I mean, everything works quite similar. You again consider quite generic dissipation. But, and then you take a quench of this parameter here, the magnetic field. And then you see this again is the same quantity, the mutual information essentially. Now you see here you have stronger scaling corrections. So you have this data for finite times and system size. But and then if you reach this scaling limit, if you approach the scaling limit, you see this deviations from the theory, which is this dashed line here, they go down, and then you can actually extrapolate and show that this is actually the case. So you get a nice 1 over L fit. So in the scaling limit, which is where this formula is supposed to hold, everything scales as it should. Okay. Now let me. I don't have time to go into the proof for the Ising chain, which has been we put this result on the archive very recently. But I can give you somehow the gist of the proof in a few slides. So as I was saying before, everything you need to know is the covariant matrix of the if you have the Ising chain of the Majorana operators. And then you have the Lindblad equation. And now this Lindblad equation, since the problem is linear, you can actually solve. You can write down an explicit solution, which is still quite ugly because you have an integral, but everything can be written down analytically. Here you have this Here you have this evolution operator, which depends both on H, which is the Hamiltonian, and on this matrix K, which from here you see encodes the dissipation. It depends on the real part of K, while here in this integral you have the imaginary part. Using translational invariance, you can write down this equation in this form, and here everything is a 2x2 matrix. This gamma K is a 2x2 matrix, this U of K is a 2x2 matrix. So in principle, you can integrate this equation analytically. And then let me consider a generic linear translational invariant dissipation. So again, due to translational invariance, you can write down the Fourier transform of this matrix K, and this is a 2x2 matrix where this function A, B, and C are arbitrary at this level. Okay, you can by varying these functions A, B, C, essentially you can address any linear translational invariant dissipation. Okay, now then you can go to the limit, the scaling limit of long times and weak dissipation. So you send the dissipation rate gamma to 0, and then you can massage this formula, and you can get an explicit expression here, which is quite simple. So you have a term which is proportional to the identity matrix, a 2x2 identity matrix, times some function C of K. You have a term proportional to sigma y K. So this sigma y are some rotated Pauli matrices, so nothing really spectacular. And then you have this term which is very important, which depend on sigma x, and then it has this time dependence here, which is the sigma y. So this is quite nice, but it's still not sufficient, okay? Because to calculate the entropy, essentially, you have to Fourier transform back and then apply this formula. And then you have to, you have to Fourier transform back, restrict this matrix to subsystem L, okay? This is this gamma L, which is restricted to your subsystem. And then you have to evaluate this horrible formula. This is quite complicated, but you can use a trick. So you essentially, you can calculate in the hydrodynamic limit, the moments, so the trace of gamma L to the power alpha for generic alpha. And then you can essentially expand this Sn, if you want, in Taylor expand this Sn, and then you get a formula like this, which depends on these objects, this trace of gamma L to alpha. To alpha because the odd powers vanish by definition because the way in which this gamma is defined. Okay, so if you know this trace of gamma L for any power alpha, and you know the analytic dependence on alpha, you can evaluate any function f, even this one. And this is the strategy to do it. Okay, it's quite involved, but you can do it. Okay. And in fact, this calculation is quite similar to what you have in the case without dissipation. So in the case without dissipation, essentially this term here is not there. And you have the gamma of k has the same form. Okay, you have some functions a and b, which of course are different in the unit case. So so the calculation is, if you want, the calculation that we did here is a generalization of this result that was presented in this paper here. Then, long story short, you can derive analytically this formula, and you can derive analytically that these terms here are given by what I presented earlier, this Yang-Yang entropies. And importantly, you determine analytically this rho of k, which is written in terms of this function ck, ak, and bk in this way. And here there are a lot of things that I should discuss. So something very interesting is that this density of k for several types of dissipations are nothing more than the densities of the original Bogoliubov modes that diagonalize the problem. For several types of dissipations, you get these densities by looking at how the Liouvillean acts on the original Bogoliubov modes. So the Bogoliubov modes remain good eigenmodes even in the presence of dissipation. Of course, the density changes. It depends on time because they are affected by the dissipation. But this is not true in general. So in general, this density is not the density of the Bogoliubov modes that diagonalize the original problem. But this formula is fully general. Also in those cases, this formula holds. Something funny that I should say now is that in this case, is actually in which this density is not the density of Bogoliubov modes. This rho of k is not an even function of k, unlike the unitary case. But you have a full solution for Ising chain under the combined evolution, unit evolution, and dissipation. Something also interesting is that these modes, they satisfy a simple rate equation, you see, which is written here. So the derivative with respect to time of rho of k is just this, okay? So it's a simple rate equation. Where these functions s, you can construct them in terms of this ck, ak, and bk. Okay, now this is enough for the global quant. So how much time do I have?
So you're into question time, and now you have around maybe 11 minutes.
Okay, maybe I can just say quickly, I can just go through very quickly discussing dissipative impurities. So this was, I mean, for global dissipation. Now I want to briefly say what happens if you take local dissipation. And here I consider a very simple situation in which I have this tight binding fermionic Hamiltonian with the gain and losses localized at the center of the chain. Now, from the technical point of view, the main observation is that since the problem is quadratic and dissipation is linear, you can write down an effective evolution equation for the 2-point fermionic function. You see, it's quite easy. And then you can solve it by a combination of Fourier transform and Laplace transform. I mean, this is not very deep, so it's well known. And then, I mean, even though something that perhaps that I want to say is that even though the problem can be solved analytically, and it's easy, it's quite easy to do, you can write down explicit formulas, but you cannot. I mean, you cannot write down very compact formulas for the correlation function. Unless you go to the hydrodynamic limit. Okay, so you have the impurity, and then you consider the limit in which time is long, distance from the impurities is large, and then the ratio is fixed. So if you take the 2-point function with the x divided by 2t and the y divided by 2t fixed, you can get some simple results, but not explicit formulas as far as, I mean, you get explicit formulas, but they depend on many details of the problem. A very simple limit that you can consider is the one in which x minus y divided by t go to 0. In this case, actually, you can rewrite the 2-point correlation function in terms of this function r of k, which has this form where gamma is dissipation rate, v of k is the velocity, the group velocities of the fermions. And if you see this formula, you immediately recognize that this is essentially the transmission coefficient, sorry, the reflection coefficient of a delta scattering. But the non-trivial part here is that the strength of the delta potential is imaginary, which reflects the fact that essentially you are putting a dissipation source at the center of the chain. So the problem is not unitary anymore. So here the central object is reflection coefficient. You can also define a transmission coefficient, and you can also define this object 1 minus tau square minus r square, which if the problem is unitary, of course, is 0. And here it's non-zero because the problem is non-unitary. Okay, and you can get a lot of results from different quenches and from different initial states. I think I don't want to discuss all the details here. So you can see, I mean, you can look at density profiles, evolution of density profiles, and I mean, you can get quite simple hydrodynamic formulas that describe this, this profile. Perhaps what I want to show, I mean, these results, I mean, there are several similar results in the literature, so I don't want to, especially a very nice paper is this one by Krapinski, who was also in the conference. Something that I think is much more new is this last result. And here I ask the question is, what happens to the entanglement entropy or the von Neumann entropy in the presence of this impurity? So for instance, I can consider the situation in which I put my subsystem A here next to the impurity, or I put a subsystem A prime that surrounds the impurity. You can actually, in this situation, you can actually calculate by using the expression for the 2-point function, you can actually calculate the evolution of the von Neumann entropy analytically, or also the Rényi entropies. Again, by using the trick, I mean, by calculating the trace of the powers of the correlation matrix. And you get this formula here. I mean, this formula here is, so this for the trace of Gn, okay, you get an explicit formula. And then, I mean, you can calculate the von Neumann entropy. But here there is a caveat that I want to make, okay? So the caveat is that essentially, due to the presence of this impurity, what happens is that there is if you send a fermion towards the origin, what happens is that it can be reflected or transmitted, okay? And essentially this means that there will be entanglement which is generated in the system. And the entanglement will be entanglement between this reflected wave and the transmitted wave. This is a bit surprising at first because the problem is with dissipation. But since the dissipation is local, what happens is that it acts as a local impurity. And even though you would like to kill entanglement, what happens is that you generate it because of the simple fact that there is a localized impurity. Irrespective of the fact that the impurity is dissipative or not, you generate entanglement. However, the von Neumann entropy is not sensitive to the entanglement. And this you can, I want to convince you about that here. So you have an explicit formula for the von Neumann entropy, okay? And this formula depends only on this coefficient A, which is essentially the probability of a fermion to be absorbed at the origin. Actually depends on 1 minus A squared, which is the probability of a fermion to survive. And this formula gives that the von Neumann entropy grows for both these two partitions. So it grows linearly with time. And this is a bit surprising because, I mean, you expect the entropy of this to grow because you have a reflected wave that goes this way, a transmitted wave that goes this way, and the two are entangled. So subsystem A is entangled with the rest. But in this case, the transmitted and the reflected wave are both at any time within subsystem A prime. So you shouldn't expect entanglement. But this formula gives you that the entanglement grows in both cases. And this is simply reflecting that the von Neumann entropy is not a good entanglement measure. Even though it's sensitive somehow, it should contain information somehow in entanglement of entanglement. Okay. And this you can check, I mean, analytically, I mean, this formula, and it works nice. So I haven't spent too much time. And then you can compare the behavior of this entanglement entropy with the behavior of the negativity. And then you see that, I mean, while the von Neumann entropy grows linearly for both, sorry, the von Neumann entropy grows linearly for both bipartitions. So the dot line is one bipartition, and the continuous line is the other one. You see that the negativity grows linearly for this bipartition, as it should, because there is an entanglement between the transmitted and the reflected wave. But for the other partition here, the negativity stays constant, which indeed reflects correctly that there is no entanglement here between A prime and the rest. So somehow this tells you that the negativity is a good measure, while the von Neumann entropy is not. And with this, I would like to conclude. I mean, I think the main conclusion is that this is really an exciting problem. There is an exciting field where there is not much that has been done, at least for entanglement. And there is a lot really to be done. And thank you for your attention. And I'm sorry for being over time.
Thanks a lot, Vincenzo, for this very nice talk. So are there any questions? So please raise your hands, and if you have a question. Yeah,
sorry, at some point, was there an assumption that the initial state is Gaussian to use this Eisler-Peschel result?
Yeah, I mean, yes. I mean, maybe I've said that is, yeah, of course, yeah, you have to be in that, of course, you have to use that, that assumption indeed. Yeah.
Jacopo.
Hello. Yes, so just one comment on the two things. So you're rescaling always the gamma to 0 as a function of L.
Yes, but it's T to infinity, L to infinity, T by L to fixed, and T by L fixed, and gamma goes to 0 as, let's say, alpha over, I mean, as proportional to 1 over T or 1 over L.
Ah, okay. So basically gamma is dynamically rescaled as you time
yes.
Gamma goes to 0.
No, I mean, you can choose, no, I mean, you can, I mean, during the dynamics, you don't rescale it, right? I mean, you choose your setup. So I want the entropy of subsystem L, okay? And then the gamma that I put is proportional to 1 over L.
Okay.
I mean, it doesn't change with the dynamics, of course, no. Yeah.
Okay. So it's just that at the beginning,
it's at the beginning. Yeah, it's fixed at the beginning.
Evolution, yes. You fix it to be order 1 over. So in a sense, it would be like 1 over size of your system.
Yes, indeed. Yes. Mm-hmm.
And okay. And the other question is because we know that indeed, as you showed at the beginning, that a lot of these formulas for entropy, they can be generalized quite easily to the interacting case. Yes. So what do you think that, did you try to generalize it to interacting cases?
Well, of course, that's the most interesting question. I'm exploring numerically what happens, but I think, the feeling that I have is the following. So, if you look at this formula, at the main formula, you see there is this this structure here. So there is this cancellation between these two terms. So my feeling is that somehow this might not survive when you take interactions. So it could be, which could also be very interesting, that in the interacting case, there is no cancellation like that. So, this formula look a bit fragile to me due to this minus sign. Because somehow this minus sign tells you that, this structure tells you that when you act with the dissipation, essentially every particle is decoupled from the other, essentially, right? Because here, this means that each member of the pair is affected by dissipation, and then its entanglement content or correlation content is essentially diminished by this number here. But in interacting systems, we know is a bit can be different, because as soon as you act on the system, it can be that all the other particles somehow are affected. So it could be that this cancellation here, this term here becomes is different. But of course, it's very difficult. So I don't know. I don't have an idea.
In a sense, you're saying that in the here the dissipation acts on a single. It's like diagonal in the quasi-particle, while in the interacting case, it's not diagonal.
Yeah, perhaps this is also reflected in the fact that at least in this limit, the initial Bogoliubov modes, they remain somehow good modes. In most of the cases, I must say, most of the cases of the dissipation that we tried, these Bogoliubov modes remain good modes. We have also cases, as I mentioned, where this is not true, but this formula still holds. But somehow, yes, I think this is perhaps
but then maybe it would work in the case that in the interacting case, if the dissipation coupled to conserved quantities,
maybe, yeah, I'm sure there is. The interacting problem is very hard because, of course, there are several ways to to include dissipation, and it's I don't know what to say. Could be that actually due to this fact that you in this scaling limit you send dissipation to 0, might be that this formula even could survive. Might be that actually could even survive in the case in which the dissipation that you add break integrability, because you have an integrable model, you add dissipation. Typically, the Liouvillean is not integrable. There are a few cases in which is integrable, but in general is not. So it might even be that since you take this dissipation rate to 0, then even though the Liouvillean is not integrable, this kind of formula will survive. But I don't have an answer for that. So it's really a very complicated problem.
Okay, thanks.
Okay, so I think we have to stop now, and so thanks again, Vincenzo. And if there are other questions, actually, Vincenzo, can you be there in the breakout room for a little while after this session?
How do I get to the breakout room?
So this is after the session. After the next talk.
I stay here. No.
Yeah. Okay.
No.
So so maybe now we break and we'll meet in 6 minutes.